You know that 5G phone in your pocket? Or your Wi-Fi router at home? Maybe even a software-defined radio if you're a hobbyist? Well, have you ever wondered what they all have in common? Turns out, every single wireless device relies on one single hidden component at its very core. So today, let's pull back the curtain and take a look at the engine that drives all of our wireless tech. So what is this hidden engine? It's called the RF transceiver. And in this explainer, we're going to break down exactly what it is. We'll look at its block diagram and get to know each and every component that honestly makes our modern connected world even possible. All right, let's start with the big picture. At its heart, what is this thing really doing? An RF transceiver is just a brilliant piece of engineering that does two main things. The name kind of gives it away, right? It's a transmitter and a receiver all rolled into one. Its whole job is to send out radio signals, that's the TX part, and to listen for signals coming in, that's the RX part. It is the ultimate two-way street for wireless communication. Now, to do its job, the transceiver has to live in two completely different worlds at the same time. On one side, you've got the baseband domain. This is the nice, clean, predictable digital world of ones and zeros that computers and processors understand. But on the other side, you've got the RF domain, the invisible, kind of chaotic, physical world of radio waves flying through the air. The most important thing to remember is that the transceiver is the master translator, the one essential bridge that connects these two worlds. So how does it actually do this translation? Well, let's follow a single piece of your data on its journey, starting as a simple digital bit inside a computer and ending up as a radio wave shooting through the air. This is the transmitter side of the story. Okay, here we go. First, our data starts in baseband processing. This is where the raw ones and zeros get packaged up, encoded, and modulated. It's like getting it ready for shipping. Next, it goes to the digital to analog converter, the DAC. This is so important. It smooths out the sharp, blocky digital signal into a nice, continuous analog wave. Then, the real magic happens at the mixer. It takes that low-frequency signal and up-converts it. Using a super precise clock called a local oscillator, it shifts the signal's frequency way up to something like 2.4 gigahertz for Wi-Fi. But now that signal is just a tiny whisper, so it's fed into the power amplifier, or PA. The PA is like a giant megaphone. It just blasts the signal, giving it the power it needs to travel a long distance. And finally, the antenna takes that powerful high-frequency signal and radiates it out into the world as a radio wave. Job done. So our data is out there, flying through the air. Awesome. But, communication needs someone to be listening. So let's flip it around and see how this whole thing works in reverse. How do we catch that wave and turn it back into something useful? The return trip starts, naturally, at the antenna, which snags that very faint radio signal out of the air. Now, this signal is incredibly weak, so it immediately goes to a really special component, the low noise amplifier, or LNA. Its one and only job is to boost that weak signal without adding a bunch of static or noise. And let me tell you, this is probably the most critical step in the whole reception process. Seriously, imagine you're trying to hear one person whisper from across a loud, crowded stadium. The LNA is like having bionic hearing that can magically amplify just that whisper without turning up the volume on all the crowd noise. If the LNA does a poor job, the original message is just gone, lost in the noise forever. A clean signal starts right here. Okay, so once our signal is cleanly amplified by the LNA, it's on to the next step. It hits a mixer, just like on the transmitter side. But this time, the mixer does the opposite. It performs down conversion. It brings that high radio frequency all the way back down to a more manageable baseband frequency. From there, the analog signal goes into the analog to digital converter, or ADC. This chops up the wave and translates it back into the world of ones and zeros. And finally, that digital stream goes into baseband processing, where it's all decoded and the original information is recovered. The journey is complete. Our data has arrived safely. Woo! We have covered a ton of ground and met a whole bunch of different components. So let's just do a quick recap of these key building blocks and then touch on some of the reasons why building these things is so incredibly difficult. So let's run through the all-stars again real quick. You've got the DAC and ADC. They're the translators between digital and analog. The mixer is your frequency shifter, moving signals up and down the spectrum with help from the local oscillator. And then you have your two amplifiers, the power amplifier for shouting really loud and the low noise amplifier for listening really carefully. Each one has a totally vital role to play on the team. And trust me, making all of this stuff work together seamlessly is a huge challenge.
Engineers are in a constant battle against noise and interference from every other wireless device out there. The amplifiers have to be perfectly linear, otherwise they distort the signal, and just making sure the transmitter and receiver are perfectly synced up in both time and frequency, it's a massive, massive headache. It really is a delicate balancing act.
So why did we just go through all that technical detail? Well, because if you can wrap your head around this basic architecture, you hold the key to understanding pretty much all modern and future wireless technology. Look at how this maps to something like 5G or software-defined radio. All the super complex digital stuff, like OFDM, which splits data across many channels to prevent traffic jams, or MIMO, which cleverly uses multiple antennas to boost speed, that all happens in the baseband domain. Meanwhile, all that analog hardware we just talked about, the mixers, the amplifiers, the filters, that makes up what we call the RF front end. Put those two pieces together and you have the complete transceiver architecture that powers our world. And that is exactly why this knowledge is so important. If you're designing wireless systems, if you're developing for SDR, or if you're an RF or modem engineer working on 5G, well, understanding the transceiver isn't just helpful, it is absolutely non-negotiable. So if you take just one single thing away from this whole explainer, let it be this. At the end of the day, an RF transceiver is that critical bridge. It's the expert translator that allows the language of computers to be spoken through the air and then heard perfectly on the other side. And that leaves us with a really fascinating question to think about. As we keep pushing the limits, as we move to 6G and beyond, with even higher frequencies and faster speeds, what new problems are going to pop up? How are we going to handle even more noise? How will we get even faster? The next generation of transceivers will have to solve all of that, and it is going to be incredibly exciting to see how they pull it off.